Hello everybody, today we're going to be answering exam 1, question 2, and we're going to be talking about topics such as osmolarity, osmosis, and Nernst equation. So let's start off with osmosis. So osmosis is the ability of water to go between membranes. And we're going to draw an example of this. So let's start off with our two membranes. So in the body we have two different types of membranes. We have the ICF, which is the intracellular fluid, which of course is the water which is inside of our body and inside of our cells. And then we have the ECF, which is the extracellular fluid, and this is the water that is outside of our cells. So the point of osmosis is that water is able to go between membranes, and osmosis is based off of an osmosis gradient, which means that water is going to go to locations that have higher concentrations. So for instance, if we add some solute to our ECF like this, you'll see now that our ICF and our ECF are no longer have equilibrium. So what this means is that water is going to flow from our ICF and go through our membrane into the ECF. And so what's going to happen is that our water in the ICF is going to decrease as the water in the ECF is going to increase to find equilibrium. And this is how osmosis works. Now, our next topic we're going to talk about is osmosis versus molarity. And so the main difference here for two words that sound very similar is what they measure. So let's start off with osmosis or osmolarity. So osmolarity's point is that it's measuring the number of solute. Now, this could be the number of solute inside the cell or outside of the cell, but the point is that it cares more about how much, whether it's like maybe 100 NaCl is inside or outside. However, for molarity's main point is the weight of the solute. So the big difference here is that osmolarity cares more about how much number-wise but molarity cares about if you have, say, a mole of carbon outside, or if it's like half a mole. And so we're going to start off with doing our 3 examples of osmolarity. So let's make our 3 cells. So here's cell 1, cell 2, and cell 3. So we're going to start off with cell 3. So cell 3 has a lot of solute inside the cell. Now this is called hypotonic. Hypoosmotic. Basically, hypoosmotic means that there's more solute inside the cell than there is outside the cell. And here's our middle one. We're going to call this isoosmotic. So isoosmotic means that there's the same inside and outside. As you can see, there's one inside, one outside for hypo, which had more inside. There was 4 inside and no on the outside. And then lastly, as you'd expect, here's hyperosmotic. So hyperosmotic is about there being more on the outside than in the inside. So here you can see there's 4 on the outside and there's 0 on the inside. Now we're going to talk about the difference between osmolarity and tonicity. So as we said earlier, the difference between molarity and osmolarity was the fact that osmolarity cares about the number of solute, while tonicity is very different than osmolarity. Tonicity is about the membrane and how much it's able to move, if it's very flexible or if it's very rigid. So we're going to do 3 examples of tonicity. So we're going to draw 3 more types of cells. So we're going to start off once again with hypertonicity. So what happens with hypertonicity is that water flows out of the cell. And so what happens is whenever you have a hypertonic cell, it shrinks. So you can say the cell is now about this size as the water went out of the cell. So next up we have isotonic. So isotonic is the type of cell you want to have. It stays the same size, and this is the type of cell which our body functions best with, as it's not growing or as it's not shrinking. And so let's talk about hypotonic. So hypotonic is when water comes inside the cell. And this can cause the cell to get bigger and bigger, and also can cause the cell to even lyse or burst, which is super bad for our cells. Something very interesting though is that tonicity and osmolarity don't always have the same prefix in front of them based on the situation. So we're going to show an example of a cell which has a different type of osmolarity and tonicity. So we're going to start off with a cell, and we're going to add 4% of NaCl and glucose to it. So here's our cell, and on the outside we have our 4% NaCl and glucose. So I'm going to represent NaCl with these pluses and glucose with these triangles. So what happens is whenever we get glucose and NaCl, they go inside the cell. And so we have our 4 glucoses, we have our 4 NaCls, and our 4 glucoses. And something that cells do very well is that they're very good at metabolizing glucose. So these 4 glucoses are going to get eaten basically immediately. Now that's very interesting, because as you can see, there's more on the outside now than in the inside, which means that this is a hyperosmotic. However, the amount of NaCl is still equal, and there's no water rushing to the cell. So that means that this cell is isotonic, as its membrane is still happy and is not getting more elastic or less elastic. It's not growing or shrinking. So this is an example of how a cell can have a different type of osmolarity and a different type of tonicity. So now we're going to transition into some of our equations that are important, and we're going to talk about resting membrane potential. So RPM, or resting membrane potential, is when the cell finds equilibrium between what's going inside and outside of the cell. And this is very important, because if our resting membrane potential changes, if it gets higher or lower, our body might not be able to function as efficiently, and we might damage some of our systems. So let's draw our cell. So cells are naturally have the resting membrane potential of negative 70 volts. And this is a super negative. And there's 3 ways that our body keeps this super negative. So we're going to start off with the first one, which is the easiest. So these are our negative proteins. So inside our cell, we have proteins that have negative voltage, and they stay in our cell and are one of the 3 ways that help us to stay so negative. Now the next one is our NaCl channels. NAK pumps. So what these do is that they're able to pump Na and K in and out of the cell. So usually they'll pump K out of the cell because K is super positive, and they'll pump Na in because Na is very negative. And this is super important because it can help increase the voltage or decrease the voltage based on how much go in and out. And now our third thing that helps to keep these so negative is what we call K-leak channels. So we have potassium leak channels that allow potassium to go in and out of the cell. Once again, these help to either raise the voltage or lower the voltage as needed. And these are the 3 ways that we're able to keep our RPM, or resting membrane potential, of our cell at negative 70 and keep it so negative. And something very important is that we have a lot of ions going in and out of our cell. And something very special about our body's design is that they have what's called a driving force. So the driving force is how much these ions want to go in and out of our body and go in and out of the cells. And there's an equation for this. So let's start off with it. So dF, which stands for driving force, equals Vm, which is the voltage of the membrane, minus Ex. And this stands for the equilibrium of the ion. So we're going to do an example with this math problem. So we're going to use Na. So let's use this. So Na has a voltage of 50. So let's start off with this math equation. So the driving force equals the voltage of the membrane, the MV, and that would be our negative 70 right here. So it equals negative 70 minus the Ex, which is the equilibrium of our ion, which is 50 for Na. So that's going to equal 50. So negative 70 minus negative 50 is, of course, negative 55 is what it is. And that equals negative 125. So negative 125 is the driving force of Na. And this driving force, with it being 125, either symbolizes that this really wants to go inside the cell or really wants to go outside of the cell. And then we have one last math equation we're going to talk about today. We're going to talk about the Nernst equation. And the Nernst equation is our last and another very important equation that we have to talk about. So what the Nernst equation does is it measures concentration of an ion either inside or outside the cell, depending on what variables we have. So let's draw this equation. So Nernst, this is E times negative 61.5 over Z, and Z is our valence. And we do this times log of X out over X in. And so when we actually have a real math problem, we'll be able to solve for our in, our out. And what these do is in represents the concentration that is in our cell, and out it represents the concentration that is out of our cell. And we can do this for ions such as potassium and chloride and all those. And that is all I have today. Thank you for listening to question 2 for the exam.